Here. Very good then. So welcome to this week's Origins Colloquium. It's a pleasure to have Macarena Garcia Marin giving the talk this week. Macarena is from the Canary Islands, where she did her first studies in physics and astronomy. She was then a PhD student in Madrid, where she was already working on simulations of the MIRI instrument on James Webb. She moved to Germany then, joining the MIRI test team, which then built and tested and delivered MIRI to NASA Goddard. In 2015, she joined the European Space Agency and then moved to Baltimore to work at Space Telescope Science Institute on the MIRI team. I think that's where I first met you, Macarena. You were extremely helpful when we were trying to prepare our MIRI proposals. Great. And then I think, of course, has been heavily involved with James Webb since that time and is now in the position of James Webb project scientist. So we'll hear about something about James Webb, I think, and also her science on James Webb's results on the galaxies. So welcome, Macarena.
Thank you, Jonathan, and thank you so much for inviting me, and thanks everyone for joining today. Can I have a last audio check? Because I cannot see any messages or anything, just to make sure.
You're good.
Okay.
Great.
So, yes, we are going to talk about JWST today. I thought I could cover a little bit very quickly the mission and the performance that we are seeing, etc. And then I decided to, because this is a colloquium, I decided to focus on what Webb has discovered on the very early universe. Kind of what are the main discoveries, where are we heading next, and then talk a little bit about local galaxies, and finally a little bit about some science I've been doing with some collaborators. So welcome everyone, and thank you for being here. Okay, so I thought I would begin by the end, essentially, just by telling you that the message here is that JWST is absolutely amazing. It's really a transformative mission. And in general, this is because it outperforms its pre-launch requirements. Images are twice as sharp, so it is fractionally limited at 1 micron instead of 2 microns. Optics are more stable, and most instrument modes are more sensitive than we expected pre-launch. And we'll talk a little bit about that later. It has fuel for 20 years, and it is now in its third year of mission. And by the way, I'm not going to have the time to cover many things, so later feel free to ask any question about the mission or other science topics, and we can have a conversation about that. JWST is truly fulfilling its promise of revolutionizing astronomy, and I think that applies to all fields of astronomy. And this is because it allows previously impossible measurements, like literally we are doing things and we are measuring things that we couldn't do before this mission. And I would like to start with this example. This is JWST 14.0, and this is the farthest galaxy, the oldest galaxy we have measured to date. This galaxy, it's a luminous galaxy that was in place before 300 million years after the Big Bang. And on the little inset in there are two galaxies. The one on top is like photobombing, the one at the bottom, that is the red galaxy. And this is truly why we launched these missions. We wanted to see the very first galaxies and the oldest galaxies in the universe, and we're doing that. Not only we are seeing images, we have this high quality spectra. And for a galaxy at a redshift of 14.3 approximately, it's really astonishing that we can see the break in the spectra and even emission lines, and we can even see that it has some chemical reactions already. So it is certainly paying off all those years of effort and development. So here you have some characteristics of these galaxies. But before going to any science, we are going to go in to talk about JWST a little bit. So what is JWST? I always like to say that truly in a nutshell, it's a large infrared optimized space telescope orbiting around a Lagrange 2 point, which is about 1 million miles away from Earth, or 1.5 million kilometers away. It is big. It has a 6.5 primary mirror coated in gold. You can see it here. It has a sun shield size of a court, tennis court size, and that is in place to protect the very sensitive infrared instruments from the radiation of the sun. And I chose this picture so you could get a sense of the size of the telescope compared with the three engineers that were just working around it in Northrop Grumman. This was around probably 2020. Behind the primary mirror, we have the science instrument module or ISIM, and in there we have nested all the scientific instruments. So we have three infrared instruments, NIRCam, NIRSPEC, and NIRIS. NIRIS comes with the guiding instrument, FGS, and we have one mid-infrared instrument, that is MIRI. Overall, we have 17 observing modes. We have different three instruments to imaging, and we have a wealth of ways of doing spectroscopy, from slits to IFUs to multi-object spectroscopy. We also have coronagraphy and aperture mask interferometry. So all in all, we have 17 observing modes. In general, I would say that JWST is a spectroscopic machine. 75% of the time, it is devoted to spectroscopy, and as we all know, that gives us a wealth of science and a wealth of information. It is truly remarkable. This was launched December 25th, 2021. It was a very optimized launch, and it is the reason why we have fuel for more than 20 years, because the launch was so well tuned with the predictions, and the injections in the orbit were so perfectly done that we saved a lot of fuel. So we have mission for a lot of decades, hopefully. This is an attempt to share with you what happened after launch. We had 6 months of commissioning, and here at the bottom you see a very high-level description of everything that happened. We're beginning at the first month, it was all about deployments. The telescope was so big that we launched it all compacted, unfolded, and it had to unfold and deploy. So that happened in the first month as we were traveling to the L2 point, the Lagrange 2 point. After that, we started a period of cooling. Everything was cooling down, and it was very slow and nicely, so we didn't have additional tensions. And then we started a long period of what we call the telescope commissioning. And that was truly, we had 18 segments for the mirror, and it was all about aligning those segments and making sure everything was working and making sure that all those segments were working as a single one. And this was the first telescope alignment evaluation image that we made public. And truly, when we saw this, it was absolutely clear that the telescope would be incredible. And as you can see in the background, not only we have the star, this was all about having that perfect star at the center, but we have also a wealth of little galaxies appearing in the background. There is nothing like an isolated star in JWST. You always have additional galaxies in the background. So after the telescope commissioning, we went into the science instrument commissioning, and that took several weeks. And by the end of that, they were all successfully commissioned, and commissioning was all about not fully calibrating anything, but about demonstrating that the telescope was ready to execute science. Finally, in June of 2022, we had the release of the first images, and I'm sure you're familiar with the beautiful Carina Nebula. That was one of the early release observations that were made public. And this was our show of image of what is how sharp the images were. Not only how sharp, but also how sensitive all the instruments and detectors were. We have a wealth of stars in those fields. And truly, I'm sure you've seen many comparisons, but I think what makes comparisons with previous missions, but what makes JWST special is the combination of sensitivity, image quality, and of course, infrared, the fact that we're working on the infrared. Talking about exquisite image quality and stability. Not only you need image quality, but we also want the telescope to be stable. We don't want the segments to be wobbling around too much. So this plot represents the wavefront error since June 2022 until a few weeks ago. So all the blue points are measurements of the wavefront error, what we call sensing visits, and the green arrows represent corrections. If the if the error increases too much, we do corrections. As you can see, we're typically below 70 nanometers, 70. Our requirement is about twice as much of that. So the image quality is really, it is really impressive, and it behaves very well. At the very beginning of the mission, there were more of those, getting off phase and then back, then getting off phase and then back. And then we had a period of relatively quiet time. And then about half a year ago, we had a big tilt in one of the wings of the mirror. And that tilt was, you can think of it as the launch and the travel to the 2 point and all that add stresses to the structure where the mirrors are placed. So that was like a great release of energy that finally made the telescope structure more relaxed. So that means that we've been about half a year without making any correction. We did one a few weeks ago. You can see it here at the very, very end. And it was really minor and not, we're not, I think we think from now on the behavior is going to be pretty much stable and on point. We do right now wavefront sensing every 2 days, and we use it to monitor the wavefront error. And it's behaving so good and it's so stable that we are evaluating currently whether to reduce this cadence and giving back science time. So talking about science time, I think one aspect all astronomers are interested in is efficiency. How much time do you dedicate to science? And within that, I think most people are interested on how much time are we using the detectors. This plot represents essentially the entire cycle 2 efficiency plot for the detectors. The blue line is the percentage of time we were using the detectors as a prime observation, and the red line is the detectors used in parallel observations. So about 60% of the time was dedicated to prime detector observation and about 20% of the time to parallel observation. So it is really very efficient. Of course, there are overheads. We have to slow the telescope, we have to move mechanisms, etc. But overall, I think, as you see here, we dedicate a lot of time to observe sky and to execute programs. Sensitivity. Of course, we want efficiency, we want image quality, but what we really want also is sensitivity. This plot, it's a comparison between the imaging modes on JWST compared with other missions and compared with ground-based telescopes as well. And we're talking about orders of magnitude, both in the near and mid-infrared. The leap in sensitivity is comparable to going from a little home telescope to one of the VLTs. It is truly remarkable, and this is what is allowing the science. I have to say this plot, it was made at the very end of commissioning, and for the most part, it has been stable except for MIDI, and I'm going to talk a little bit about that shortly. This is a sensitivity for the lines, the spectral sensitivity, the line sensitivities, and again, orders of magnitude. And not only that, but we have never had this spectroscopic power in space, covering all these wavelengths and covering all these, offering all this variety of observing modes. I forgot to mention, and I'm sure many of you know, but on the near infrared, we cover about from 0.5 to 5 microns, and the mid-infrared covers from about 5 to 28 microns, both for imaging and spectroscopy. So I mentioned that for MIRI, things have changed at the longer wavelengths between the end of commissioning and now. So after commissioning, we realized that at the very long wavelength, for MIRI, both for the MIDI MRS, the medium resolution spectrometer, that is our IFU, and the imaging, at the longer wavelengths, the sensitivity was decreasing. There is a reduced count rate. For the imaging, as you can see here to the right, it is stable now. So it was mostly affected at 25 microns, and it was a reduction on about 22%, 20%. But that is now stable, and the behavior is very predictable, and it's not changing anymore. For the medium array, especially at long wavelengths, at the very long, between about 25 and 28 microns, the decrease has been significant, more than 50%, and that is reflected on this line here, and the others are more, like 20%, and a shorter wavelength is really not significant. So that behavior, again, was more significant, but is now getting stable. It has stabilized for all bands except 4C, and 4C is getting there. So we have a flash calibration program that monitors a trend, and we have a model that predicts a trend, and we don't see significant deviations from the model. So what we do now is when we have a call for proposals, everyone who uses our exposure time calculators will have the prediction for the end of the next cycle. So we are very confident that your predictions of the ATC will work perfectly fine. The root cause remain under investigation, and if you're curious, we can talk a little bit about that later. So this was, of course, not desirable, but my main message here is that despite of this, MIRI is producing amazing science, and the MIRI MRS, I think, is one of the most transformational instruments we have on board, because it gives access to a wavelength range, not that, well, it was explored by Spitzer, obviously, but not at that level of detail and sensitivity. And you can see here the forest of lines we are obtaining in many test cases and the high quality data. So anyway, let's talk about a little bit about science. I just wanted very briefly to remind all of us about what are the 4 pillars of JWST science. The main reason why this telescope was built, as I mentioned before, was the early universe. The driver was to observe the very first galaxies that were created in the universe and the very first stars, and you can only do that on the infrared. The second pillar of science, it's all about the assembly of galaxies over time, how those very early galaxies evolved and became the galaxies that we have today. We're talking about galaxies that have to grow hundreds of times bigger, and lots of changes and evolution. So that is one of our the second pillar of science. We, of course, also have the birth of stars and protoplanetary systems. There is a lot of interesting science going on in there. And finally, planetary systems and the origins of life. For this presentation, I'm going to focus on galaxies and mainly on the early universe. What has JWST discovered? What have been the big, questions we are answering, and what are the additional questions we are now having because of those new answers? And I'm going to move also into the more local universe and just very briefly share a few highlights in there as well. So this is the usual cosmic time for the universe. We have the Big Bang to the left, we have the cosmic microwave background, the dark ages, and then finally we begin the reionization where the first stars and galaxies were formed. So understanding how galaxies form and evolve, it's a really tall order, if you want, because we're talking about 13.8 billion years of cosmic history, and that requires a lot of data and a lot of application, a lot of model and theory and combination of all of that. This is how the same diagram looks like, but here, as you can see, there's more emphasis on the first giga-year of the life of the universe. Again, you have the Big Bang, the CMB, and then at some point, and we don't quite know exactly when that was, the first galaxies and stars were formed. So the beginning of reionization is not a line we can mark as of now. We know that GNC 14.0 is younger than, it was about 290 million years after the Big Bang it was there, but is that truly the very first galaxy? Probably not. So there's still a lot more work to do, and I'm sure that will be, we're going to push that limit. But anyway, first stars and galaxies, and then after that we start seeing pockets of reionization. We see many galaxies being formed, many stars, and then the environment changes and grows until we have the galaxies that we can see on our universe today, the local galaxies. So we're going to talk about this period and what are the big discoveries. So JWST has revealed what I would call a robust population of high-redshift galaxies. This diagram, it's very good. So the top diagram, the x-axis is the redshift. So we are going to very high redshift, and the y-axis is the magnitude. So in blue, you can see the sources that we knew were there pre-JWST, mostly with Hubble. And then on orange, you have the more than 1,000 galaxies that we have spectroscopically confirmed using a combination of near-spec, multi-object spectroscopy, and near-cam wide-field slitless. So we've seen a lot of objects. Many of them are very bright. Many of them are very old. So this was not expected. We didn't know there would be so many in there. If you now then look at the bottom diagram, another very interesting finding that is sort of a challenge to answer, like why are we seeing that, is the fact that JWST data is inconsistent with the stars forming from gas clouds with constant efficiency. So on the bottom plot, you have this gray line that goes down. That is a model that predicts constant star formation efficiency. So until redshift of about 10, I mean, it works relatively well. Like galaxies are kind of more or less following that trend very nicely within error bars for the most part. But then from redshift 10 on, and definitely with the recent JWST results, you can really see that these galaxies do not follow a constant star formation efficiency. So the question is, why? And I have to say, many of these questions are not answered yet. It's just an ongoing investigation. Not only we're finding these very many galaxies at high redshift, but JWST has also revealed a very bright, very rare galaxies at redshift larger than 10. And this is represented in this very nice diagram from Carniani. So in this diagram, the red squares and also the red pentagon, they are spectroscopically confirmed galaxies. The pentagon is just from a different sample, but it is also spectroscopically confirmed. So in here, we're seeing that the 4 galaxies that have their names written in there, they are 4 spectroscopically confirmed superluminous galaxies at redshift larger than 10. These are located in the Goods north and south field. So we're talking about a relatively small cosmic volume. We're not talking about, these are all the galaxies that are on the sky. This is relatively small. So this is an indication that probably there are more, but it's an indication that there's probably a time-specific physical process responsible for these very bright galaxies. Like, why are they there? Why are they so bright? Why solely at that period of the universe? And this is probably related with, as I said, some time-specific physical processes, probably related with the onset of cosmic dawn, with the beginning of reionization. So what are the theories going? What are the potential answers for this? Well, one could be that in the early universe, there was really very high star formation efficiency. For instance, feedback-free starburst or compact star formation. That could be a potential explanation. We could have a top-heavy initial mass function, probably with very massive population 3 stars. It could also be due to ejected dust. This is from a work from Ferrara and collaborations, where they put together a model where the dust is expelled from the galaxies, probably due to star formation. So they are cleared out of dust very early in the universe, and then they shine very, very bright. And then finally, versus star formation could also be responsible for these very, very bright objects, because it would enhance in particular galaxies, the star formation in that period, and then we would see it brighter. Which one it is, we don't know yet. Maybe it's not only one, maybe it's a combination of factors. Sometimes things are not neat and well defined, but these are some of the explanations that are on the table right now. There's also a lot of conversations about cosmic reionization and what were the sources that drove that reionization. And it is clear that a fraction of it is probably driven from AGNs. Some authors saying that it could be up to 50%, at redshift of about 6. But this comes with a large uncertainty, as you can see in the plots here. But it could be up to 25%. So AGN were contributors to the reionization. But the truth is that there's still significant debate about what is the primary source of reionization in the very early universe. In particular, the contribution of faint galaxies, it's still to be explore and determine because we haven't seen them. So what this means is that we need even deeper observations with JWST where we actually see more fainter galaxies and then can understand at which level they contributed to reionizing the universe. So it is, again, an open field, but a really exciting one. We cannot talk about AGN and JWST and not mention the little red dots, and I'm sure some of you are familiar with this. So this is a new population of galaxies discovered with JWST, and there is that, again, debate or tension. Are they AGNs? Are they driven by all the stars? Are they only one thing, or are they a combination of things? Still to be confirmed. But what they are is that they are very compact red sources, several hundred light years radius, so it is a lot smaller than our own Milky Way. So they are small, they're compact, and they are very red. This is here an example from a paper from 2023 where they took an H-alpha selected sample and they found that and they did spectroscopy, and they found that the majority of these little red dots in their sample had broad lines. And they suggested a population of dust attenuated AGN. So that could be one explanation. Other authors have actually modeled, this sort of V shape between the red and the blue, and they have concluded that they can model these objects with an 80% success rate for AGN. However, we cannot do this only on the near infrared, and this is where other teams are coming in and saying, well, we also have MIRI, so we need to observe the same objects with MIRI, and then understand if the mid-infrared is telling you something different. And actually, some of them are finding that with MIRI data, the dusty AGN model is over-predicting it, and actually the SED is much better or generally more consistent with the presence of an old stellar population. There are also conversations about selection effects due to, you use colors to select some of these objects, etc. So again, an open field. And I think this is one case where little red dots are probably not a single thing. They are probably, some of them are AGN, some of them are driven by or dominated by all the stellar populations. It's not the case of a neat and clean-cut solution, but certainly a very fascinating problem to have, and one that we didn't know we had there before JWST. These objects were discovered with this mission. The fact that we have so much spectroscopy gives us an incredible tool to attempt to understand chemical enrichment, metallicity, and how did this all occur. So traditionally, metallicity is determined using strong line ratios, for instance, between oxygen 3 and H beta in the optical, that are calibrated locally. However, this may not work at high redshift if we have different ionization conditions, which could very well be the case. And I mean, as you know, the gold standard calibration is oxygen 3 because it is sensitive to electron temperature. So anyway, this is all to say that some groups are now working on the concept of, okay, we're starting to have a significant number of spectroscopic data for high redshift galaxies. So they are stacking this data and building spectroscopic templates that are representative of high redshift star-forming populations at different redshifts. So they're building up beams of stack spectra at different redshifts and trying to understand the metallicity and the chemical richness for this case. And this is one of those such templates. I believe this was for about redshift of 5. And in this case, here is the oxygen 34363 line that is blended with H gamma. So this team then they construct gas phase oxygen metallicities as a function of redshift for the stacks they derive, and you find them in here. And here this red line represents solar metallicity. So this is truly a promising prospect to trace chemical evolution in a statistical way, which I think it's always more robust than just having like a single galaxy here and then another single galaxy there. So again, this calls for, as usual, more data, more spectra, a larger pool of information that we can actually stack and statistically understand their significance. So this is a promising field. But talking about metallicity, of course, we need to talk about population 3, because again, this was one of the first, along with the first galaxies, the measuring and discovering the very first stars, the population 3 stars, it is one of the primary objectives of the mission. We're still searching for them. These are the stars that were made with a very pristine hydrogen helium only material, and we have not still, there has not been a publication that has, in a robust and unequivocal way, identified population 3 stars. But there are some claims and there are some promising paths to understand and study these objects. So this is a Maiolino publication on GNC11. GNC11 is one of the most fascinating, brightest, massive objects we have out there. And they see, or they claim, an isolated helium-2 line, this one here, near the GNC11 nucleus. So it is a little blob in there. And the claim here is that a population source with these 6 to 10 to the 5 solar masses could ionize helium in this way. And they also say that it is physically too far from the AGN to be ionized by the AGN. So this, in combination with the absence of metal lines, is why they claim that. However, it's not a very robust or solid claim, and I believe they are going to follow up with another proposal that is already accepted to try and in a more robust and solid way determine that, yes, this is a population 3 source. We'll see. The other interesting discovery in this area is discovery proposed or claim for population 3 comes from Vancella in 2023. And this is based on NIRSPEC IFU spectra of a highly magnified source at redshift of 6.6. So in this case, the way they are approaching this is that they don't see oxygen 3 on that source. And that puts strong upper limits to the metallicity, and they find that it could be very, very poor, 0.003 times of the solar metallicity for a 10 to the 3 solar mass system. Again, not fully confirmed, but an indication that they are there. So like in many other areas for JWST, when it comes to the early universe, probably population 3 discoveries will not come from a single galaxy and a single team. I think it will be a combination of techniques and different objects and different researchers working on that and finding paths to truly indicate that, okay, we know what the population 3 stars are. I also have to say that this is really a challenging measurement because there are models that predict that these population 3 stars, they were very big and they evolved really, really quickly in a matter of a few million years. Probably they are already chemically reached, so they are hard to measure. Anyway, another fascinating area of research that we can pay attention to. I would like now to leave the very, very early universe and highlight a couple of results from more local universe that I think they go again in the direction of having statistically significant samples that also draw from other missions or from other telescopes, in this case, ALMA. The logo is cut on there, but the x-axis is for ALMA. And this is a very nice work that talks about observing dust in normal galaxies beyond the local universe, which is something that we couldn't do easily before JWST, to observe dust in normal galaxies, dust in high redshift galaxies. And it's funny because back in the day, redshift 1 used to be high redshift because at redshift 1, the age of the universe was about half of what it is. And I know now we all think about redshift 10 and all that, but redshift 1 is still a faraway galaxy that can be challenging to measure before JWST. So in this very nice work, they use MIRI to see that the dust is linked with cold gas in galaxies. So essentially, the correlation between CO and dust, it is nicely followed. And these points here, the points that are little circles with black around, this is the new data that has been added to this plot. Essentially, the plot before that was seeing a correlation between the CO, the dust and the cold gas in galaxies, but it was mostly using local Eulers, bright galaxies, maybe high redshift galaxies, but much brighter. So this work has focused on normal galaxies, normal star-forming galaxies, and they also follow this correlation, which could point to a universal relation. Unfortunately, because of the redshift and the wavelength limit of MIRI, because it stops at about 28 microns, we cannot go further in further redshift. So still, this is solid, and this is up to redshift of about 4. We're seeing that this relation actually holds, and that local galaxies and high redshift galaxies, no matter what the brightness or no matter what the star-forming rates they have, they do follow this correlation. It's very tight.
So
I
maybe
personally love this image.
5 minutes.
Eh?
Is it okay?
Yes, I'm going to end in 5 minutes.
Great. Thank you.
Thank you, Jonathan. Very nice image. Nearby galaxy where we actually see all these bubbles and structures that are the effect of star formation. And I'm putting this, I mean, this is not, the slide is from Janice Lee, but essentially it's a funny one because you here have a case where a theoretician to the left is saying, hey, finally, guys, you're observing things that are following my prediction with models. So truly, we are resolving with JWST small structures up to bubbles, shells, or filaments everywhere in nearby local galaxies. And I just wanted to highlight the FANS project, where JWST is truly revealing the physics of star formation, feedback, explosive activity, etc., etc. So they have a sample of over 100,000 star clusters to work with, and they are doing great strides in that direction. Finally, this is the last sense case. Just wanted to highlight the studies of local galaxies with interferometric spectroscopy, where you can truly study at a sub-kiloparsec resolution and resolve, in this case, in Marcaria 231, the nuclear star cluster, nuclear star burst, and also, in this case, identify that it is at the center of a large, massive rotating disk, that it has widely spread low velocity outflows. So very detailed studies that are made possible because of JWST spectroscopy, also in local galaxies. All right, so in summary, JWST revolutionizing astronomy. Some aspects of our understanding of galaxy formation are being placed under pressure, if you want, by findings, but of bigger and brighter galaxies, but still, this is a very exciting time to study this field. It's a very exciting time to use JWST, and Cycle 3 programs will continue pushing the envelope. I wanted to finish with 2 quick things. Just to remind you that JWST is high in demand by the community. The community has broken the record of submissions twice already for Cycle 3 and Cycle 4. So here you have the previous record, ALMA Cycle 6. JWST broke it. Well, the community broke it 2 years in a row. We have many proposal submissions for Cycle 4, and the time allocation will be 8,500 hours. The demand is likely to grow, and the size it will keep growing. So if you haven't submitted a proposal, don't forget that Cycle 4 will likely be in August 2025, August 1st. And finally, if you're not subscribed to our JWST Observer News items, please snap this QR code and subscribe. You'll get news about the observatory, pipeline updates, calibration updates, proposal-related news, anything you need. And there are lots of resources in there. So just thought I could close the talk with that so you can get informed. And
Great.
this was my last slide, Jonathan.
Thank you very much.
Thank you.
So we have plenty of time for questions and discussion now with Macarena. So raise your hand in the
Let me
Zoom.
stop sharing so I can see you.
Yes. But you may, of course, want to show some slides if they relate to questions and points.
Oh yeah, definitely. I can. Let me see if I can share and still see you. Should be able to.
But please raise your hand in the Zoom if you have a particular question, and then maybe I can start with a few things I was wondering about. So, of course, you talk about mainly about the high redshift galaxies. Has MIRI, what is the highest redshift object that MIRI has studied? I'm just
The
curious.
same one, actually.
Uh-huh. So,
So it's this one,
yeah,
JWST 14 in imaging,
in imaging.
but in
Right.
imaging, and then in a spectroscopy, it has been a galaxy at redshift of about 12 with a MIRI LRS.
Mm-hmm.
And I
And
know there will be attempts to do this galaxy in a spectroscopy with MIRI too.
mm-hmm.
It's doable, it just requires time,
Mm-hmm.
obviously.
And well, I have lots of questions really, but then some relates to the presence of dust then in the galaxy. So is the dust continuum must be the continuum that is seen from the dust in this object? Is that
Yeah,
right?
yeah.
So because you mentioned one of the models for these early galaxies is dust being blown out of the galaxy.
Yeah, yeah, it is right. It's attention, right? So it can either be they're very like the little red dots. They are probably very dusty, and then the dust glows in the infrared. But this model proposed by Ferrara is more like, well, okay, maybe what if uh, the dust was just blown away from the galaxy, and
Hmm.
then you don't have any extinction in there, and you can see
Hmm.
all that bright luminosity.
Hmm.
It's a model, and it's a very theoretical model in the case, but it fits well with the data.
Right, but if you're seeing dust in the galaxy, doesn't that mean the model is either has a problem or we can just forget about it, or is it
Yeah,
expected?
that's a good point, actually. Uh, yes, it could be,
Uh-huh.
but yeah, I'm trying to think. It's all about how you interpret it. So I think many of these observations are, the photometric points, when you measure the points and then you fit your model. And I think when it comes to these high redshift galaxies, you have to rely on your models. And then it's when it gets complicated because some things can be, oh God, some things are fitted well with, large amounts of dust and some others not. But
Mm-hmm.
in the case of so this model from Ferrara is not applied for the little red dots that we think are very dusty. That
Mm-hmm.
is more for the very early galaxies at high redshift, much higher redshift.
Mm-hmm. But that is one of these here where you're saying there is dust detected in the. Now, this would not be counted as a little red dot, is that right? Because this.
No, this is not.
Uh-huh.
No. And
Okay.
and this is, I hope that was clear, but it's only the galaxy, the little red. Let me just move to the next one.
Yeah.
Here is clearer. So there are two galaxies here.
Uh-huh.
This one is just contaminating. This is not, it's this
Uh-huh.
one. And actually, when the team started looking at this subject, they initially dismissed it because of the contamination, but they kept working on the data and it really paid off to,
Mm.
to clear it up.
Well, I had a related question on these objects then about you mentioned the line widths. So if you have Miri spectroscopy, you'll have to remind me what kind of velocity resolutions you have and what kind of lines are being seen in these kinds of objects and what kind of line widths are being seen and how they compare to
We don't have mirror spectroscopy for these subjects,
uh,
as far as I know. It's all, yeah, we only have the Zavala for the Redshift 12 galaxy. So for that we have.
mm-hmm.
And we think, don't trust me on this, but I think we're seeing thousands of kilometers. Right? But I would have to check that. But the bulk, I have to say, the bulk of the spectroscopic results at this redshift is, as of now, with NIRSPEC. It's on the near infrared. And
Yes.
many of them, this is what the type of spectrum and quality we're getting. But I think the MIRI will come next.
Mm-hmm.
I think people will be moving into the mid-infrared because it is the next thing that makes sense to add that component to really understand what's going on, which is the case, for instance, for the little red dots. you need the mid-infrared to understand if your AGM model really fits with what you're seeing in the mid-infrared.
Hmm. And we have a comment from Al. I don't know, Al, if you want to just speak it.
Well, isn't this object with
Yes,
O3? Yeah, from
yes,
Elm.
you're absolutely right. Yes, there is O3 ALMA spectroscopy that came out not so long ago, I think. So yeah, they have oxygen 3 detected.
Hmm. Hmm. Redshift at
At redshift of
14.
14.3.
Wow. Hmm. Great.
Yeah.
Ryan has a question. Great.
Yes, thank you for the presentation. I had a quick question about the stacking of the spectra. Are you stacking, is it hundreds of galaxies you're stacking, tens? I'm just curious of, the level of improvement in signal to noise you're getting from stacking
For
X.
this one,
Yeah, how many sources are getting stacked in these plots?
well, it's not me, obviously.
Yeah.
It's a different group, but I'm trying to think because I read that I think they're stacking tens of them
Okay. Okay.
in bins. Yes.
Okay.
Uh,
And that's enough to reveal new lines or detections of.
well, it's enough to improve
Yeah.
what they have and maybe to get rid of undesired noise. I mean, you see here the 1 sigma error. It's on the light blue. So I'm trying to think because at this redshift, especially if you separate them into bins, we don't have, especially at the very high end, we don't have, hundreds of objects.
Mhm.
We have, let me go back so we can. So if we're talking redshift 8, 7, 6, there are plenty there, but then depending on the redshift, as you move further, then you have less and less. So it really depends on the redshift being you're trying to attempt. But I think I really like that approach of saying, well, okay, let's try to do this in a statistically significant way.
Right.
Is the
Do you know if
noise
anyone?
moving as you'd expect when you stack then?
Yeah, I think so. I mean, you can see here that the error bar gets bigger because they get less and less galaxies. So
Hmm.
that has an impact on their
Hmm.
metallicity estimations.
And just very,
So
have people been doing that with the little red dots at all to see if they can kind of help reveal the nature of those, or has it just been for the known galaxies and
I
things like
well, the little red dots, no, I don't think this has been
that?
done for
Okay,
the little red dots. No,
thanks.
but it could be. I think yeah, it could be, but they are very strange animals, so I don't know if I would put them on this.
Right, right.
Yeah, I don't know that what I like about all these early universe investigations is that it's truly so new, everything, right? That you can find creative ways and like it often happens, I think the answer for many of these questions, it comes with we need more data.
Can
We
I just
need more.
related to this then, can you give us a sense of how much telescope time is needed to take a good spectrum of a redshift 14 galaxy? Or what kind of, are they asking for 10 hours or 100 hours on one source?
Typically well, this is near spec MSA, so you get more than one source. But it is hours. I think up to 100 hours could be in some cases.
Hmm. And again, the noise is scaling as you'd expect, or is there some?
In this case, yeah, it is scaling. And I mean, I don't have, unfortunately, any other near spec example here, spectra, but even if you look at this guy, right?
Mhm.
This is the spectra, the 2D at the bottom of the detector, so it is noisier. But when they extract it, sort of collapse on that, it is noisy, but it's not. I think it's amazing considering how far away the galaxy is.
Mhm.
But yes, when you go to redshift of say 10, 9, 8, the noise is very much reduced, and you could see it visually. You don't have to do any analysis to see how it gets better and easier to get it.
Okay, great. Ruben has a question.
Yeah, well, thank you very much for the nice talk, Macarena.
Thank you, Ruben.
I so happily that you mentioned that indeed James Webb will be 20 years, no, of life. And my question goes in that direction. Initially, I thought it was like 10 years, I think, and then the launching was so exceptional that we can double the life. But is there any chance to actually have beyond 20 years? Like, I'm thinking of a warm mission or something. Can you say something more about it?
A war mission, that's interesting. So as of, I like that.
Well, I
This
guess for Miri, maybe it doesn't make sense at all because it's too bright, even at few Kelvin. But I wonder for the your
near
medium
infrared.
infrared instruments if they will be like a warm spitzer or something.
Okay, so the fuel is what we know now it will limit. The sun shield protects the near infrared instruments. So the sun shield is 5 layers of very thin material, and we are out in space. So you could expect that, there are maybe micro perforations, and perhaps those micro perforations end up letting additional radiation coming through and increasing the temperature. And this is why we track very, very carefully the backgrounds. There's a lot of work going into that, and there is a mild increase that we're measuring now, but so far it's going well. So to answer your question, I think if the temperature was to increase, the near infrared instruments would see the impact earlier in the longer wavelengths, like 5 microns, etc. And then perhaps they will lose that before losing the short wavelengths. The funny thing with MIDI is that because MIDI has its own cooler unit, maybe it wouldn't be as affected by that. And this is me, just brainstorming. But you could think that okay, because MIRI has its own cooling unit, maybe it could stand a little bit longer. But certainly, if the temperature was to increase and if the MIRI cooler couldn't, then certainly MIRI would be the first one that
Right.
it has to be at 7K.
Are we going to be in a situation like in the Hubble that we were for a few years, and now next year will be the 35th anniversary, or is not the case for James Webb?
I hope so.
What do you think?
I really hope so, and I think, as I say, right now the limiting factor we are aware of is the fuel, and that's a fact. And the fuel, I'm always amazed with the operations team and the flight dynamics team, because they're so good at optimizing. So yes, we have fuel for more than 20 years, but I'm confident they will find ways of optimizing and manage the momentum in different ways. So it gets, we can extend it as much as possible. However, when the fuel runs out, slowly the telescope will drift out of orbit, and then we will lose it. And that would be the primary limiting factor for that. It's equivalent of Hubble going down its orbit far away, and it needs that fuel to keep it in there.
Great.
Okay, thank you.
Let me come to you showed a graph of the great stability of the trying to remember exactly what is the metric on the accuracy of the mirror. Yes. Does this define then the size of the PSF, or is it also?
Yes.
Because I'm particularly interested in astrometry applications. So, how I assume there's some distortion solution for the whole image plane, and my question is, how stable is that, and how well characterized is that?
The PSF?
Well, the PSF, but also I understand there's some distortion solution, isn't there, across the field of view of the instruments?
Yes, there is a distortion. Yes.
And
yes. So
is that stable, or is that, do you have to characterize that every few months, or?
It is typically characterized once a year, the distortion from the instrument teams. So we do the wavefront error every other day, but that's usually, for the most part, you use a star at the center of the field, of the field of view, and you use NIRCam for that. But then, of course, the NIRCam team, they have their, as you said, the distortion that covers the entire field of view. sort of they correct for that. And typically there was a lot of work in commissioning, but then once a year there is a checkup on that. And I think there are always attempts to improve the distortion solution, not only for imaging, but also for spectroscopy. For instance, if any of you has been using NIRSPEC IFU data, you would be aware that the distortion solution is not optimal at places. So the team has gotten a lot of new data to optimize it and get it better. So I would say calibration is never a finished work. For whenever, if you have a 30-year mission, you will be 30 years calibrating it. And you get better and better, but never perfect. So you always want to keep doing that. And part of calibration is monitoring. Sorry.
Is there a Miri distortion solution then? I'm just curious as well.
Yes, there's a Miri distortion solution.
It's all done separately as well.
Yes, it is, and it is available as a reference file, essentially. We didn't talk because of timing. I didn't want to go into pipeline or anything like that. But if someone has questions about that, I'm happy to talk about it too.
Well, let's have one more question from Ryan, then I'll close the main session, and we can maybe have an informal session right after, if that's okay. So Ryan, please go ahead.
Speaking of calibration, just one quick follow-up. So the sensitivity declining of Miri, you think it's stabling at this point?
It is, yeah.
Thanks. Okay.
So in imaging, I can confirm it's fully stabilized.
Okay.
So the Miri team has a very solid calibration program to monitor this. So in imaging, it's stabilized for the MRS. It has stabilized for most channels. In 4C is still getting there. So I cannot claim full stabilization, but it's very minor. Yes, if you're curious about the root cause, we really don't know 100% sure, because you launch this thing in space and then you cannot go and open it up and see what happens. But we have evidence that for the MRS, part of this has been due to darkening of some of the dichroics due to the impact of radiation. So that's probably why it's more impactful on the long wavelengths of the Miri MRS, because it just happened to affect the dichroics in the Miri MRS and just at those wavelengths. There were suspicions of maybe the detectors being partially responsible for this effect, but the test that was executed didn't really provide a conclusive answer.
Well, it's amazing the instrument and the whole facility is performing as well as it is, that this is really the only...
Yeah.
Right, we're at the hour now, so let's thank Macarena again.
Thank you.
And I'll stop the recording.